Right, we're just going to start off then by recapping just some of the basics that we've done so far. I mean, we're very, very close to the end of this unit, and next week, next Monday, we will be starting the other chemistry unit, what we used to call advanced chemistry. This one was our sort of introductory chemistry, and then the other one advanced. The difference between them is, well, the advanced one, the second one, does require you to understand everything that you've done in this one. It's not assessed directly, but without all the things like the conventions of writing formulae and being able to use moles and things like that, you can't cope with that second unit. So, there's no way you could do them the other way around, for example. That one, the energetics, kinetics and redox, is 3 different things. It's 3 learning outcomes, it's 3 assignments, and it's 9 credits. Right, so it is a big one. It takes us through the rest of the year. And we are going to make a start on that next week, and it will launch straight into some of the work that we did before Christmas on this unit, which is the energetics bit, where we started talking about enthalpy. So we did a bit of scene setting. You've got that bit on bond enthalpies in the assignment, and we move on from that and we do some practical measuring of enthalpy changes, and the first learning outcome picks up from that point. However, we've still got a bit to finish off for this particular unit, the bonding, reactions and organic chemistry. And this is really, it's reactions and it's organic, and it's to do with organic reaction mechanisms. But before we get into that, just want to quickly recap a few of the things that we've done. With the organic section, overall, I don't want to sort of recap everything that we've done, but with the organic, we met various groups. So we had the homologous series, didn't we? Different homologous series. So we had things like alkanes, alcohols, and so on. We did the idea of isomers, and then we've touched on some of the reactions and aspects of those reactions. So we've looked at particularly the energetics side of it. So that was it was a bit of an excuse for sort of putting that in. And the other thing that we're now going to do then is to look at the mechanisms. That's where this is coming in. All right. So that's not a particularly good recap there, but just pulling some of the bits out that we've covered there in the last few weeks before Christmas, that was. We also need to sort of go back to some of the earlier stuff that we did in the bonding section. So if we think back to the earlier part of this unit, the section on bonding required, first of all, a decent understanding of atomic structure. So what we were looking at particularly was the electron shells. Right? We weren't too fussed about the protons and neutrons, but the electron shells were rather key to the formation of bonds. We also considered things like electronegativity, first ionization energy, and electronegativity particularly was telling us something about the sort of bonds that would form. So we had types of bonds, and we had our non-polar covalent, and that's the one really I'm going to come back to in a minute. But just for completeness, we also had our polar covalents. which has been pursuing us around through biology as well. We've had ionic, and then we also had the intermolecular forces. I put that up there because they're significant in the assignment, aren't they? You know, when you're looking at the melting and boiling points, you're looking at intermolecular forces. And the idea of the non-polar covalent bond is the one that we've got to think back to. And something that I only introduced, I don't think we did it in any detail. I did mention Lewis structures, I believe. Does that ring a vague bell? Using dots, yeah? You've got, I think there's a handout on Lewis structures, and those are quite handy for drawing some of the electron movements that are going to be important. Well, they form a good basis for it. It's not something I'm particularly, I don't use it a lot. I'm not particularly sort of fluent in using Lewis structures, but we can go back to that handout if we need to. But the idea is that you show how pairs of electrons are shared, or how they're arranged. You're only interested in the outer electrons, the valence electrons, the ones in the outer shell. And if you were going to draw, for example, hydrogen, you've just got 1 in its outer shell. Chlorine has got 7. So if we were to react together hydrogen and chlorine, if we were going to draw it using the Lewis structure approach, you do that. All right. And obviously, that's not chlorine. Sorry. Whoops. And we wouldn't be looking at single atoms of them either. We'd be looking at molecules. So we'd have H2 and Cl2. So this is not really very helpful at all at the moment. But if we were reacting a single atom of each together, what you have then is your bond, that's where I wanted to get to, represented by that pair there. All right, so that's your shared pair in your covalent bond. And I could have done it just quite simply. I suppose the easiest one to do would have been hydrogen itself, wouldn't it? You know, a hydrogen molecule, H2, is where you're sharing 2 electrons, 1 from each atom. So you've got a covalent bond between them like that. Similarly with chlorine, this will only really work if I use 2 colours, won't it? So let's do black ones around this one, like that. And then if I do the other chlorine atom as having red electrons, which of course it would like that, then our shared pair in the middle. That's the idea of the Lewis structure. So they can be quite useful to see where the outer electrons are and where the sharing takes place. Now these are not the only sort of options for drawing the atoms and their electrons in bonds, but you know, in terms of understanding what's coming up, these can be quite helpful sometimes. So the covalent bonds that we were drawing, we were drawing the circles to represent the actual shell and putting little dots or crosses on those. But I think these are a little bit tidier to use sometimes. The only problem is the amount of space, because they can get a bit cramped. We also had this idea of single and double bonds, and I seem to remember we had a problem with the board the day I was doing that. So I'm just being drawn towards the flip chart, having talked about double bonds. I think the problem was solved quite quickly. You get this idea of the single bond where there's a single pair of electrons being shared, but we also have, right, so these are, you know, single bonds, and these are known by a Greek letter. They're sigma bonds. The sigma bonds are the single ones. If, however, you've got two pairs being shared, so for example oxygen, where we've got how many in the outer? 6, yeah. So, whoops, that's not going to work, is it? Sorry, you have to excuse my head. It's not functioning very well at all. Right. Sorry, this is me being a bit disorganised. We'd have a double bond there, so they've each got their own 6, but a share of 2 from the other atom. So that's a very messy one. I'm not good at drawing Lewis structures, I must say. When you look at this in organic chemistry, the most common place that we're going to be meeting this is between carbon atoms. It's the unsaturated bonds that you get in the alkenes and the double bond. You've got 2 components to it. You've got one pair that's shared sort of directly between the 2, which is the sigma bond, and then the other one is the pi bond above and below. Yeah, so it's sigma and pi. So sometimes you see it drawn so that you've got carbon. Let's see. It's probably got 2 other things. You know, if we had a bond like that, the actual double bond in that arrangement would actually consist of a pair of electrons forming the sigma bond. So I'll put the line in just to sort of show where that is. That's the sigma. And then the others, the other pair, are found somewhere above and below. Okay, so you've got that is your sigma pair, and then this is the pi pair or bond. Now, they're really important when it comes to looking at some of the mechanisms. One of the mechanisms involves this sort of arrangement, because those pi electrons are very vulnerable. Because they're above and below the main bond, they can very, very easily be attacked. So they can be removed quite easily and taken away somewhere else. So that's our single and double bonds. Just other things that we've done. Generally speaking, we haven't really looked at reactions in the sense of electrons moving about. We've looked at reactions in the basic sense of reactants and products. But how do you get from reactants to products? Well, when we did the energetics bit, so this is the final bit of recap, so reactions generally, your reactants turn into your products. But in order to do that, when you start with your reactants, you have to separate the component atoms to some extent. And this was the sort of general principle behind the bond enthalpies calculation that you did. And if you took this one, this molecule here, it's the ethanol molecule here, C2H5OH. If we were burning that, as it is in your assignment question, then you have to put in energy to break those atoms apart to start with. Now, if you're breaking the atoms apart from each other, you're breaking bonds. And if you're breaking bonds, you're changing or you're moving electrons, aren't you? Because we know that a bond is, in this case, shared pairs of electrons. We're not talking ionic bonds here, we're just talking covalent. So in order to break a covalent bond, we've got to be moving electrons about. So for the reactants to go into the products, we've got bonds being broken along the way. And then in the products, we've got new bonds formed. Now, because bonds are all about electrons, all right, that's a little bit messy there, but we can now extrapolate, if you like. You know, we can make some assumptions, make some suppositions that if we're going to react two compounds together, then we know that electrons are moving. And we can identify which electrons are going to move and where they're going to move to. That's where curly arrows come in. So if any of you have looked at curly arrows and thought, yeah, can't do that, you know, it's not as hard as it might sound to start with. But, you know, if we look at the electrons as they are, particularly in double bonds, it's perhaps easy to see that electrons might move. Then, you know, that is what a reaction's going to be about. So, what we're going to start with, on this first bit this morning, really, the next half hour or so, we're going to do a bit of slogging through some of the sheets in your handouts, two of them particularly. You've got one which has a big question mark in the middle of it. All right, so you've got a big question mark in the middle and then 4 boxes around the outside. So find that one. And it's headed up Key Ideas in Organic Chemistry. So we're going to have a look at that. Then we're also going to have a look at the next one, which presumably is on the other side of yours, which is Reactive Sites and Organic Reagents. And I think that might be as far as we get this morning. We'll see how that goes. Then after lunch, we'll move on to, you've got drawing mechanisms. And this, if you have a look at that, you can start to see these curly arrows. Yeah, and you can see lots of little dots and, yeah. We'll talk a bit more about those. And if you go then sort of further than that, you'll see lots of examples of organic reactions, a lot of which we're not going to do. And then it gets onto a sheet which I have no idea why I included that one, except really to show you that if you were to go on and do a degree in chemistry, this is the sort of thing you actually have to learn. You have to be able to, predict all sorts of different reactions. It then goes on to using curly arrows in reaction mechanisms, which is, you can tell, well, I've written at the top, taken directly from Chem Guide. Thank you, Uncle Jim. And then it goes on to free radical substitution, gives you an example. And we should have at the end electrophilic addition, and those are the 2 that you need for your assignment. All right, so, yeah. However, they do, I've given you slightly different versions of them, but yeah, Chem Guide is exceptionally useful. It's just that you need to write it in your own words. Right, so let's have a start with this then. The Key Ideas sheet. I'll keep track of this on the board for those who aren't with us at the moment. But if you refer to your Key Ideas sheet, we will have a look at the boxes on there, and we're going to start on the left-hand side and work our way around anti-clockwise, I think. I have no idea whether that's a sensible order. It doesn't number them. First of all, if you've got a large organic molecule, let's take, for example, something I've got sitting on the desk that I keep waving at you, this one, which is, that's the glucose one, yeah. All right, a glucose molecule. Now, we could say, will glucose react with anything? Well, what do we mean? You know, are we talking about the whole molecule? Clearly not. And will glucose react with anything? Well, yes, it will, actually. One of the first things it would react with in a cell, if we take a biological example, would be ATP. You can phosphorylate glucose. And the glucose acquires phosphate groups from ATP as part of the first steps in respiration. It sort of activates it and then it releases a lot more ATP by you know, that process having got it started. And the phosphate groups become attached to particular carbon atoms in this. Okay, now this is 6 carbon atoms which we can number, which I think starts at this one here and ends with the one that sticks out on its own. So this is carbon 1, that's carbon 6. And I think those are the 2 where the phosphate groups get added. They don't get added anywhere else. Right, so you get something called glucose 1,6-bisphosphate. So they get added to this one and to this one. Why just to those and not to any of the others? Well, this one over here is attached to an oxygen, so that's clearly a vulnerable point for a reaction. This one sticking out on its own has got a, you know, it's not attached to another carbon over here, so that's presumably more vulnerable. So, you know, we've got reasons, but it doesn't attach to carbon 2 or 3 or 4 or 5. I think I've got that right anyway. It attaches to carbon 1 and carbon 6. All right, always, nowhere else. So there must be parts of molecules which are targets. And that first box, you can see it says reactive sites. So that first box is just sort of saying, well, you know, there are particular points on molecules which react, but there are also the rest of the molecule probably won't. You could, for example, take, let's take a little ethanol molecule here, 2 carbons, as opposed to, let's say, the decanol molecule that you do a comparison with in your assignment. You know, is there a difference? Well, yes, and it's in the carbon chain, isn't it? And the hydrocarbon chain is very unreactive, actually. The bit that reacts is the OH group. Right, more than anything else. And, you know, we could pick up any of the models that we've got and identify reactive sites. So the first thing that we have to consider is reactive sites. We're not going to spend ages and ages on all of this, and I'm not going to write loads of additional notes. I'm just sort of summarising as we go here. The first thing that we've got here then are 3 situations which might create reactive sites. These are not the only ways in which reactive sites come about, but if you're trying to find a bit on a molecule that might react, then consider these things. First of all, is there a difference in electronegativity that gives you this charge separation? Now, we talk about charge separation in terms of polarity, don't we? Polarity particularly relates to when you've got hydrogen involved, but charge separation essentially means the same thing, doesn't it? A positive bit and a negative bit. Yeah? So you've got this idea of charge separation. Now, if you've got a bit that's positive and a bit that's negative, so delta plus or delta minus, then you know you've got a bit of a molecule that's not balanced. It's got a bit more of one sort of charge than another. So it's a target for something, isn't it? Second option there is our double bond. Well, there's a surprise. I've been rather setting the scene for that. And the thing about the double bond, of course, is the fact that you've got this pi system that you can see drawn there as a little cloud above and below the bond. So where you've got the left-hand bit of that, carbon to carbon with just 2 straight lines, and then 2 lines coming out, and then drawn in more detail, you've got the additional bonds coming out of the carbons. You've got a dotted line and a wedge. I don't know if you've come across those anywhere. The dotted line is a bond which in 3 dimensions is going away from you. A wedge is a bond coming towards you, all right, with the thick end towards you. So it's just as though that's drawn in a sort of 3-dimensional plane there. And then the third option, do any of the atoms have lone pairs? Lone pairs are pairs which are not involved in bonding. All right, so lone pairs, there will usually be some lone pairs there. So they've drawn those out with little rings around the pairs on the oxygen. All right, so that if that was, I mean, that could be anything. It's obviously intended to be an alcohol. It could be methanol. The carbon could just have 3 hydrogens attached to it there. Bonded to an oxygen, which is bonded to a hydrogen, but the oxygen there has 2 lone pairs. So those would be targets. All right? So this idea that molecules have particular parts that are going to react. Right, the second point on here, what attacks what? Okay. So the what attacks what is a bit about terminology really, because we do have different sorts of target, therefore we have different sorts of attacker. And you have 2 here. You have nucleophiles and electrophiles. Now, a nucleophile will attack electron deficient regions. Okay? Now, electron deficient means lacking negative charge, so that means it's got more positive charge. So you can see the little diagram that they've got there. The carbon attached to the chlorine, well, the chlorine will have stolen some of the electrons. If you look at that, it's the same one as was right up at the top in the reactive sites box, where carbon's got an electronegativity of 2.5, chlorine's got an electronegativity of 3.0. Consequently, you end up with a delta negative on the chlorine, it's more electronegative, leaving the carbon as delta positive. So that has set up a charge separation. So that's now a reactive site. And because the carbon has this slight positive charge on it, it will be attacked by anything that's carrying electrons that can be given away. And so you've got on the left-hand side there in that little box this idea of the nucleophile, which is a nitrogen with some other stuff attached, but it's got a lone pair of electrons, and they are attacking the slightly positive carbon, and that is a curly arrow that's in there. All right, it's showing the movement of a pair of electrons. Now, we haven't met the curly arrows properly yet, but if you get a curly arrow, an arrow with a curved stick, and it's got a full head on it, it's representing the movement of a pair of electrons. If you get a curved stick with half a head, it's representing the movement of a single electron. So that one's just representing the movement of a pair of electrons off that left-hand compound, whatever it is. I think could be ammonia. And it's attacking the positive part of that other molecule. All right, so you've got nucleophiles. We're not doing nucleophiles. But, you know, you get nucleophilic reactions. The other one, electrophiles, is a little bit easier to understand. The phile bit means like, doesn't it? So nucleo, you know, when you think of the positive charge in the nucleus, nucleophiles are drawn to positive charges. Electrophiles are drawn to electron areas, electron-rich areas. And you can see that the description there, the little diagram there, shows a positively charged NO2. Not sure what you'd call that, but that's the plus has actually sort of moved down. It should be higher up than that. NO2 plus. It would be a nitrite ion, I suppose. But that's drawing electrons from the pi system in a benzene ring. Now, you'd have to go back to last term's bits to check up on that. But the circle inside that hexagon I'll just do a quick reminder. Benzene. Oh, that's not what we wanted. Okay, the board over that side is not playing the game. Might be alright over this side. No, I think we've lost. Funny, it's been fine. Okay, I think we're going to have to. Right. How peculiar. Right, I'll just put this on pause while I reset the board. Fingers crossed that's a little bit better. Yeah. No, is the answer to that. This is going to turn it off and on again. Right, I won't try and do any more on there at the moment. The benzene ring thing, look back to the end of last term, because when I did that, I introduced the idea of the pi bond. It's because the formula for benzene is C6H6. C6H6? Yeah, and you could have alternate double bonds between the carbons, but they move about essentially so that what you end up with is a pi system above and below the 6-carbon ring. Okay, right, whether I'll be able to add any more onto this, I don't know. I think the whole computer's going to have to go off and on again. I think it's possibly because when I started it up, it was actually updating the smartboard software anyway. However, we'll give it a go. The next box round is mechanism. So let's just give this a go and see if it will have it. Doesn't look promising. Oh, that is different. Okay, can't be having that. I'm going to stick it on pause again while I deal with this. Okay, the board is refusing to play ball, so I will just talk through the rest of it. And I might have to use the flip chart and maybe take a picture of that and stick it on the smartboard. This idea of the mechanism, then, we've got one of the things that people don't realise is that you won't just get a reaction between two molecules that are sitting side by side. They've got to be moving about, and they've got to collide with the right bits making the collision. I can't think of a really good analogy for this, but if let's say you were playing Pass the Parcel or something like that, think of an easy analogy, a children's game, and the reaction is denoted by the parcel passing from one person to another. Well, if you've got to pass it across from hand to hand to hand, and that's the only way that it works, and you're sort of sitting at arm's length, well, it's not going to get passed from person to person if you are sort of sitting back to back, for example. Because when your hand goes out to the side, it's not going to meet the next person. So you've actually got to have the reactive site to make a collision with the whatever's going to attack it. So the things that were in those two last boxes, reactive sites and what attacks what, have actually got to come close to each other. You can't have a reaction between non-reactive parts of the molecules. So we've got to get them aligned correctly. So you've got the example that was in the top of the what attacks what box. You've got an example there which is just using a nucleophile, Nu there, just representing any nucleophile, will give up its pair of electrons to what's gone wrong there? Have a look at the other thing in that reaction. There's something wrong with it. Compare it. Yeah, the positive and negative are the wrong way round, aren't they? Yeah, the carbon should have the slight positive charge because that's what the nucleophile is attracting, or attacking, I should say, whereas the chlorine will have the negative charge, yeah. So you can change that. So it will be successful as long as the nucleophile is attacking from the carbon end. However, if it attacked from a different direction, if it came in from the other diagram shows it approaching from a different orientation, shall we say, that doesn't work. I'd have it approaching from the chlorine myself, but there we go. Electron rearrangements, if they can rearrange, then it will happen. If you're asking it to do something impossible, then the reaction won't take place. And then you've got other considerations. How stable is an intermediate? Will the activation energy be high or low? Will the reaction be slow or fast? These will all be determined by things like the orientation, the energy required to move the electrons about, and so on. So we'll look at the mechanism in more detail later anyway. I will top up the notes on the notebook file when we're done with this. The other box on this sheet then, will the reaction work? This one, we're not so concerned with this because we are just going to look at reactions that will work. We move on to studying feasibility of reactions right at the end of the course. It's a separate sort of thing. But we've got things like how good is the nucleophile or electrophile? So, some are better than others. Some are more aggressive, shall we say. If you come down, you've got how reactive is the site. So, for example, the double bond is more reactive than the carbon to chlorine arrangement. Can the attacking particle get in? Is there space for it to actually get in there? Is there, the word there, steric hindrance? Steric, think of stereo. Steric is to do with shape, yes. So does the shape mean that things get in the way? When you build these models, sometimes you've got a lot of beads all sticking out in the same sort of area. And that then doesn't necessarily mean you can get something else into that space. So shape of the molecules can be important. How strong are the bonds? Will they break easily? We've looked at bond enthalpies. So a bond with a lower bond enthalpy will break more easily than one with a higher one. So carbon to bromine has an enthalpy of 276 kilojoules per mole. So that will break more easily than a carbon to chlorine, which is 338. And then other things like how stable is the leaving group. So if you are losing something from a molecule, how stable is that? They've got an example down at the bottom. So H2O is a better leaving group than OH minus. So that's sort of key ideas. So what we're looking at is, that a reaction doesn't just happen, that you have to consider which bit of the molecule is going to react, what sort of reaction is it, what's coming in and either stealing electrons or donating electrons, the mechanism we're coming back to, and then will it actually work? Can the molecules actually get into each other? Is there enough energy available to break the bonds, and so on? All right, so this is making the picture a little bit more complex. We're looking at more details here. Okay, now the other sheet I wanted to do before lunch, we are not going to spend so long on. And again, I can't put the notes on the board at the moment, but I will sort of fill that out a little bit once I've restarted the computer. So this second sheet, reactive sites and organic reagents. I have no idea what order to do this in. If we start, I don't know, start at the top left again. A lot of this is really just sort of elaborating on what we've had on the previous sheet. So functional groups and reactive sites. Now, functional groups are those bits that actually identify a molecule. Let's say, a double bond might identify an alkene. An OH group will identify an alcohol. A COOH group will identify an acid. So those are what we call functional groups. And it says there, functional groups control the chemistry of molecules because they contain reactive sites. So if you're looking for which bit of a molecule is going to react and it's got a functional group, chances are that's the bit that reacts. Okay, so it's a good starting point. The two kinds of reactive site in a molecule, it then gives you electron deficient sites and electron excessive sites. And we represent those by the delta plus and delta minus. Delta plus if it's deficient in electrons, so if the electrons have moved away, then we're left with a slight positive charge. If we've got electrons moving towards, then we've got the slight negative charge. And so, we're either accumulating electrons or losing electrons. Those are most likely to be the reactive sites. So we've got some examples there and some diagrams. So things like ions, a pi system, lone pairs, difference in electronegativity, these are all now things that we've met. Right, where to go next? Let's just go anti-clockwise again. Again, this is filling out from the previous page. So classifying organic reactions, we can classify by the type of reagent. And this is where, on the previous page, we identified this idea of nucleophiles and electrophiles. So nucleophilic and electrophilic. But there is a second way of classifying them as well. And this is by what's actually happening, what you're left with, what the product is. So what happens when the reaction is over? So we have options like addition. Well, it's not difficult to work out what that might mean. Addition would be something extra being added to the molecule, an atom or a group. You might lose something, so you could call that elimination. So those are the reverse of each other. You can replace one atom or group with another, in which case we've got substitution. And these are the three most common types of reaction. And then if you combine those with the nucleophilic electrophilic options, you've got, it says on the next pages you'll see examples of. So you can then, you put those together, you get things like nucleophilic substitution, electrophilic substitution, nucleophilic addition, electrophilic addition. It doesn't really work quite so well with elimination. That just sort of stands alone. We also have a free radical substitution to look at. So they're named according to the reactant that's used and what actually happens overall. Right, I'm going to go up to the top right, actually, the reagents. These, again, it doesn't sort of add a huge amount, but the substances then that are used to make the reaction, things like bromine, water and sodium hydroxide, classified by the kind of reactive site they react with. So, not surprisingly, nucleophiles. Nucleophiles are particles with lone pairs of electrons. So these are ones that are going to be attracted to positive parts of molecules. And good bases are usually good nucleophiles. That requires you to know what a good base is, but it doesn't matter. But these lone pairs, you've got them there on NH3, there is ammonia. N bonded to C is CN, cyanide. H, that's actually got a negative charge on it, it'd be a cyanate ion. OH, there, it's an OH minus, so it's a hydroxyl ion, and hydrogen with an extra electron is actually a hydride ion. They're not very common. We usually talk about H plus ions. We've then got down the bottom electrophiles, and you've got things like reagents that are attracted to regions of negative charge are electron excessive sites of the electrophiles. And sometimes a dipole is induced or caused by the compound it's reacting with, making an electrophile. So an electrophile is an electron pair acceptor, and you've got bromine as an example there. Now, bromine doesn't normally have a dipole because it's two identical atoms sharing a pair of electrons. So, yeah, depending on the charge separation elsewhere, then this is what you can have, sort of induced by a neighbouring particle. Sorry about sniffing on the recording. I will have to stop soon. You've then got your final box down here. I left this one till last because this leads us into the next step, the reaction mechanisms. Now, so during a reaction, we know that our bonds are broken and made. That's something that we've already met, and that's where we went with the energetics bit and the bond energies. Hence, why I packaged this lot all together. There is a logic to it. You might have wondered, why did that bit of energetics suddenly appear? It's related to this. The bonds then are attractive forces between positive and negative bits of particles. God, you don't often see it written like that. Making and breaking them means moving electrons around, which was pretty much where I started, wasn't it, with this? So this next bit is the important part. A mechanism is a description of a successful collision between the reactants, okay, which is a reagent particle and the organic compound particle, and the electron rearrangements that happen as reactants are changed into products. Most mechanisms are a series of 3 labelled diagrams. Right, and they show the particles at 3 very, very specific points. You don't just make these up. You don't put lots of intermediate steps in. There are just 3 steps. So the first one, just before a successful collision, and therefore lined up properly. So you're showing, before any reaction has taken place, what's bonded to what and how they would be lined up. Secondly, during the collision as the electrons are moving, so that's where the curly arrows are particularly important. And then after the collision, what you're left with. All right. So once we start drawing our reaction mechanisms, then that's where we're going to need the curly arrows. And they're particularly significant, when we're looking at what happens during the collision. Okay, that is the sort of background to this. I think my head is getting so congested now, and my voice is starting to struggle a little bit. So I'm going to stop at that point, and then we'll pick up this afternoon with the rest of this section, which will be to look a little bit more at the use of curly arrows, so that you can see how they're actually being used to represent the movement of single electrons or pairs of electrons. And then we will go straight on to the 2 examples that you need. And then you shouldn't have any problems actually finishing that assignment off, to be honest. It's not as difficult as it might look at first glance. Yes? Well, you can do, but basically I'm going to tell you what the assignment is this afternoon. So, right, let's stop this for now. And then I'll save this bit as is, and then I'll restart it again this afternoon with the right bits on it.